Hello and welcome to Risc-V emulation in a high-level language. In this episode, we're going to be continuing our work on the assembly language parser that we've been working on for the past few sessions. And we're going to start hooking things up and trying the program on a real image and or a real program. And I thought we will just jump straight into this. So in our driver program, we in the current state of the project, we have this C# simulation of an assembler. And what we're going to do is we're going to replace this now with this text assembler that we've been working on the last couple of times. So we will write text assembler here and then correct all the errors. First of all, since we're reading the source text from a file, these instructions are no longer necessary, so we'll just discard them. That was easy enough. And then, of course, we need to pass in the correct parameters to our text assembler. Now, it needs the byte image of the source file that we're going to assemble, so we'll need to provide those bytes. And the way we do that is by reading them from the file system. So let's just do that. Read all bytes. And we'll read them from the path, which so happens to be, let's see, that's 3 levels up. And the program is called echo.asm. Now, having read all the bytes, we can now feed them into the assembler. There we go. Now we have an assembler. Now we're going to ask it, please assemble the whole file. And if you recall, this will return a section, an assembler section, if everything went well, and a null if there was an error encountered during the assembly. So we'll hang on to this, and we will then say if the section is null, then we'll write some error, console.writeLine errors were found, stopping assembly. Something like that. Maybe that's too verbose. But in any case, at this point, we will return because there's nothing else to do. Maybe we can return an error. No, we can't do it that way. Okay. So in a future iteration, we'll fix that. I want to return a number to indicate that the assembler failed. But when you're writing in this functionless mode in C#, you're not allowed to return a numeric value, and that's okay. But we'll go back now and see that if we do have a section, then we want to feed that section into the linker. We also want to pass on the symbols, and then we also have to pass on any relocations that we may have accumulated. And of course, we don't have any of those in our text assembler yet. And the simplest solution to this is to just pass through the relocation list from the underlying assembler object. So we'll go to our text assembler and add support for this. So we'll add here. We have a list of relocations, but that's just going to come straight out of asm.relocations. Similarly, our symbols are going to come straight out of asm.symbols. Like that. And then we will no longer need this. So that's good. And then we also are going to need to know where exactly the assembler is positioned currently. So what we'll do is we'll go to the assembler and expose its instr pointer as a property. I'm going to call it position. like that. And then we can look at where we are using the section in this piece of code, and we'll ask the asm for its current position when we define a symbol. And now we can even say asm dot add symbol, and we'll pass in the name as before. And then add symbol returns an error if the symbol already existed. So what we want to do then is check to see if this is null. Now we want to report an error. And I'm going to introduce a new method called error, where we write we'll have a common place for reporting all of our errors and keeping track of when an error has occurred. So this new error method will take a string, which is the error, the diagnostic error, and then we'll say duplicate definition or redefinition of symbol, and then the name of the symbol. And if we run into a symbol like that, we can probably just continue the assembly. But now, having written error, we can now log the error in a useful place. And we'll do it like the other ones where we say error and then the line number and then the message itself. Let's give that a better name. But also, what we want to do as a side effect here is to set the valid flag to false. And now we can find all the places where we're doing this and change them to call error. And then we will have one common place for reporting all of our errors. Oh, and I found a bug. Skip until is supposed to skip until we reach a particular token, but we're not doing that. We're actually skipping only until endline. So let's call this a better name also. Stop token. Yeah, skip until the stop token. Okay, that was much better. We no longer need the add symbol method now. We've moved that over to the old assembler, so to speak. Okay, any more dot valid? Unexpected is another source or another consumer of error. Let's fix that as well. And I notice that this should be a cast or character because otherwise we'll be printing out a number. And what we want to do here is print a user-friendly character on the screen. All right, any other more? Let's see if we find any more valid. That's it. Okay, nice. So let's now let's try building this and run it and see what sort of output we get when we run it on our program. Here we go. And Visual Studio Code never ends disappointing. Okay, let's just close the shell and go back to here. Let's see if we can recover some sanity. Here we go. All right, so now let's run it. See if we can get it to build. Let's go. It looks like, no, we're very good. We're just very slow again. Wonderful. All right, let's try launching this now and see whether we can get this to execute. We have a few breakpoints set here and there. Let's get rid of those. Oh, well, this is not very helpful. We're throwing exceptions. We should be using our new error method. So let's use that. Error. That's a lot more helpful. And then let's return true instead. But also let's use that skip until end line so that we can make some progress. All right, let's try this again. And finally, we have some actual output that will guide us in our implementation of the remainder of the assembler. So notice that we have a whole lot of syntax that we haven't implemented yet. We don't know how to handle minus signs, and we also have a lot of instructions that we need to implement. But then also we don't know how to handle strings. So let's attack these problems in order. So a minus sign, when we encounter that, we're currently not expecting complicated symbols or expressions. So what we'll do is we'll assume that if we see a minus sign, we will always expect it to be followed by a number. And that will be good enough for now. In a future version of this assembler, maybe we can add expressions in the assembler. But for now, I want to satisfy myself that I can handle negative numbers as well as positive numbers. So we need to add a unit test for this because we want to run this safely. So let's find a number test right here. Okay, so let's add a test then for a negative number. And so we want that to be -1 now, and we want the result to be -1. And if we run all of our tests, this is going to fail. And so we need to look at our assembler and see how we can handle negative numbers or the negative sign. And the first thing that we do is we look at the start state. Remember that when we're reading tokens and reading white spaces, we're in the start state. If we do see a minus sign, then we will want to shift into a new state that we're going to call minus. So if we see a minus sign, then we'll change our state to state.minus. And continue our looping. Let's add that to our enum, and then at the end of our switch statement, we will add another state called minus. Now if we see a minus sign and it's followed immediately by the end of file, then we will write unexpected for now because we're not expecting that. let's write case -1 then for the end of file, unexpected, and then the, well, error. Actually, it's the minus sign that we are complaining about. So we'll write unexpected and then minus sign. And then we will return end of line. All right. Now, if it's not a minus sign, then it better be a digit. So we will check the case for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is basically going to be the same thing as the case when we detect a number. So what do we do there? That happens over here. So we want to do pretty much the same thing. But we also want to keep track of the sign. So what we'll do here is we'll say current value equals this and that, but we also will have a variable called sign, and we're going to set it to -1. And in the beginning of the function, by default, if you don't see a minus sign, then the sign is going to be 1. Okay, so now we have a sign we will initialize ourselves to have a sign and then proceed processing the number. However, at the end of the processing of the 3 kinds of numbers that we have, also we need to handle all the other cases here. So if we see a minus sign and we don't see it followed by a digit, then we currently will just stop or yeah, return an error. Although maybe don't return end of file. Maybe we instead return. Maybe we just continue in that case. We'll just keep grinding. In fact, we can do that in both cases. So let's just do that. So if we encounter a minus sign followed by either the end of file or some other symbol that is not a number, then we are in unexpected territory, but we do continue. I'm happy with that. Now, every time we then return a token.number, we will have to multiply the current value by the sign. So here we have to say current value multiplied by the sign before we return to the caller. And let's find all these places. Here's another place that we have to do the same thing. And let's find another one. Same. Oops. They're all now preceded by the sign adjustment. So if I run my tests now, I'm expecting that test to now pass. And it did. Excellent. So now that we have that, if I now run the program, we should no longer see a minus sign as a problem in the errors. And now we can start working on the next error, which is the store word instruction, which we haven't implemented yet. So let's look at what a store word would look like. And let's see, we have a test here that we could genericize. You know what? I am going to move these genericized tests further down the file here so that they're a little easier to locate. And so here's add needs to be converted to the same format as the other tests. So we'll just say run test, passing in the text of assembler language program, followed by the programmatic assembler that we're using as a benchmark to compare against. We're making the assumption that we did a perfect job in that assembler, and maybe we did, we'll see. And that should still pass. Let's make sure that that is indeed the case. And then we're now going to add support for store word. So store word is going to be very simple. Let's just grab a store word from our sampler program. Let's see here. Let's grab one of those. And let's put that in our unit test. And we don't need the comment. We know that we can handle them now. And then this is the equivalent of m.sw 10 to 0. So we'll follow the pattern that we've been following, where we implement a handler for this particular class of instructions. All the store instructions follow the same class. They're the instruction class S. But let's run our test first of all to say that we will get an error. We expect to get an error now because we haven't implemented SW. And there's the error. So now let's go fix it. So in our text assembler then, looks for add I. Here's our slot for SW. SW is here. And we need a new method called asm_s to assemble a S-type instruction. And then we need to go and find the place where the old assembler is doing an S-store word. So let's find that. Here's our store word. So we'll steal this and go back here and take the opcode we just need the opcode for this and then asm_s. Get rid of this garbage, and now we are ready to add a new method, asm_s. Now what should asm_s do? It's going to look very similar to asm_r, or actually probably more similar to asm_i. So let's grab asm_i. So in asm_s, we're actually reading the source variable, then we're reading the base register, and then an offset. And then we're going to call the underlying assembler. Ooh, interesting. How did we call store W or store word before? There is an asm. Oh, yes, but it's private, and we need to make this internal so that we can call it from the outer assembler, the text assembler. Asm_s, now it takes the opcode, and then we take our three variables, which are the source, the base register, and the offset. Good. So if we run our unit test now, everything should be good. Let's try it. Let's see if that indeed is the case. All right, good. So now we run our big program. A lot of those errors will now have disappeared because store W is a common, or store word is a common instruction in our program. Now we get to jump. And jump will require symbolic support. And this is where we're going to start adding references to other parts of the program. So what we'll do is we will write a unit test where we say jump, and we'll jump to some symbol like my label, say. And what we expect is that this um, generates some output, just like this would. But also we want to verify that a reference is generated. So let's change run test so that it returns the text assembler that we are testing. And then jump um, will return that into a variable. And then what we'll do is we'll ask the text assembler, we'll assert that tasm.relocations.count is equal to 1. So we got one relocation request, and also that that particular relocation that its symbol name is my label. And also we want to assert that the relocation type is equal to the jump PC relative relocation type, because this is a jump that we're doing. And now if we run this unit test, of course it will fail because we haven't implemented the jump instruction nor the relocation facility. But we will reuse what we wrote in the previous assembler, the inner assembler. But let's run the tests. We'll grind away in the background, and in the meantime we'll go to here. Now the jump instruction, we'll need to have a special handler for it. So we will add it here. So if we encounter a jump instruction, we will grab the opcode is here, and ASM J to assemble the J instruction. Okay, good. And so the J instruction takes only one target. Now remember that J is actually a sort of a shortcut or a pseudo instruction for the JAL instruction when the destination and the source are both 0. So we'll need to take that into account. But we'll grab this and then go back to our ASM J, and let's go to ASM R and use it as a starting point. So private static void ASM J is a text assembler, needs an opcode. All right, find all the places where we call this. Should only be one, and there's our opcode. So now what we do is we're going to grab the next token, and the next token in the text file should be a symbol. So we are going to expect a symbol or a word. And we don't have a method for that. We have expect number, we don't have expect word. So let's write expect word, and that will return either a word if a word does follow, or a null, or actually an empty string if it doesn't. So we'll say that the symbol is expect word, and then after we've gotten the symbol, we can then go back to our ASMJ and do the following. Emit a relocation, and then emit a jump. But this is a private method, so we need to make it internal. And this is also private, so we need to make that internal. And then we will pass in the opcode. Like that. Good. And then emit relocation, we need to specify the current position of the assembler, which is going to be asm.asm.position. And then the target, I guess we can rename this to target. And all you have to do now is implement expect word, and expect word is going to be very similar to expect number, except it will return a empty string if it fails. And then we say if get token is not equal to token number, then we'll say expected a symbol. Well, let's call this expect symbol. And then, of course, if that fails, we return the empty string. But if it didn't, then we return this dot get token string. Good. Right. So now we need to call expect symbol from our code, which was here. All right. Good. Let's try our unit test and see whether we pass. Right, so we fail. Now why is that? So we have an error in our output. Okay. Let's try to figure out why that is. Oh, we are out of sync. We expect an end of line here as well. But let's run the unit test inside of the debugger, and let's try to find the error when it gets set. So this is the place where errors are set. Let's put our breakpoint here and run the test and try to see why we are failing. Okay, we are failing. Expected a symbol. Interesting. Why are we not seeing a symbol? That looks like a symbol to me. Alright, so maybe there's something wrong with our tokenizer. So let's put a breakpoint on get token or read token. Let's see what's going on here. So let's stop, go back to our test, run it again in the debugger. Let's try to figure out why it's so unhappy here. So here is the first token. That's going to be a jump. So after reading that first token, our token is a word, and the word is a simple J. Good. Now the next token is being read, and that token is space, space, space. Here's our beginning of the token. And here are the successive letters being consumed. Let's put our breakpoint on either here or here. Those are the only places where we can read this or leave this. Okay, so there's our word. Nice. And now we have a token. But our expected token was colon. Okay, that's fine. We leave the loop. And now we find the encoder for ASM-J. Okay, let's find the ASM-J definition. Let's put a breakpoint here. This is the place where we're failing in any case. Let's run there. Okay, we single step in. And now we read another token. What was the previous token? Previous token was a word. And I'm blind. Okay, so this is the problem. We're expecting a word, not a number. Cool. Let's run this again. Make sure we're not breaking anything. Okay, great. So we are under control. We're back on track. We continue to eliminate instructions and other tokens that are failing. Let's get rid of the breakpoints that we added. Don't need those. Okay, so what's the next? So now we need to implement load word. And now this is going to be quite familiar. So we add a unit test for load word. We can steal it from store word, I guess. We'll just use a similar unit test for load word. And load word looks familiar, and we expect the same results. Now let's run our unit tests, and it will fail. And while it's running the tests, we'll go and implement the actual fix. So load word is going to be similar to store word. We'll have a new ASM, encoder load word, which will take the opcode for load word and then ASM, well, let's see, what format should we be using? Let's look at load word here. It's an I type instruction. Okay. So we'll grab the I here and or the opcode, and then ASM I will be the encoding for L for a load word. Let's run our unit test with this new code. Passes. So, next instruction. Branch equal BEQ. I guess we know the drill by now. We want a BEQ now, so we'll grab the test that we wrote for jump and we'll steal it to use our BEQ test. So BEQ, now BEQ compares two registers for equality, so register 1 and register 2, and if they are equal, then we go to my label, and we'll do the same thing in our older assembler, and then we will verify that the encodings are the same, and naturally this test will not pass, and so we will now implement that in our text assembler. So here we go again. BEQ, new ASM encoder, BEQ, and we'll steal the encoding opcode from here. There it is. And then we will ASM B is a new method now that we need to implement. So ASM B Actually, we need a variant. Yeah, so yeah, we will handle this. So BEQ would, actually, do we have another implementation of BEQ? I am surprised because, here they are. We need to steal this as part of the branch handling in our code. So as am I, sorry, as am B, and this would be text assembler. So what we want to do then is we're expecting two numbers, so those are our registers. And we'll call them reg1, reg2. And then we need a target, which is going to be a symbol. So we're going to call that asm.expect symbol. And then we will emit a relocation. Where we pass in the current position and a relocation of type BPC relative to that destination, and then we assemble the actual instruction using our old trusty assembler from before, reg1, reg2, and we need to make this a internal method so that we can use it from this class. Then we need to go back to our unit test and make sure that we're testing for the right relocation type, which is not J, but B PC relative. And we run our unit tests. And it fails. And it fails because there was an error. So now we need to figure out what the error was. So let's put a breakpoint in our error function. Right here. And let's run our test under the debugger. Oh, we didn't compile. Or did we? No, we did compile. Oh, we did not compile, and that's why it's failing. Okay, stop right there, and then run it again. This is annoying. I can't seem to be able to stop the Visual Studio Code. Its integration with the debugger is not always working or in the way that I want it to. That passed, wonderful. But if I go back now, yeah, it's still trying to run those tests. So let's see if I can refresh the test and have this stop. I'm not sure whether this is a bug or if it's something that I did wrong. I'll cancel the test run. Doesn't seem to have any effect. Okay, now it did. Here we go. Let's go. Let's make it build. BQ is now implemented. Nice. Okay, so we continue. Now, hopefully we will reach... Oh, there's another instruction, AIUPC. Well, let's implement that. So AIUPC is, AIUPC is special. So let's take a look at the source program for AIUPC. So AIUPC is using this new directive called PCRel high, which is the way in which we indicate that we're going to be loading the absolute pointer to the space object in two parts. So we need to implement a way to handle this expression here. This is an expression. We have a directive followed by a parenthesis and then another expression, which is a symbol. So this has to be implemented in we'll create a new method called immediate operand and use that to parse expressions of this kind. So let's go and add the unit test first. So we expect that. And then here in our tests, we will add a UIPC, grab it like that, run the test, and we want this to be the assembly language syntax. You know what? I want to follow the assembler, the Risc-V assembler manual. I'll put a percent sign here to make it clearer that this is a directive, and then we will have to augment our assembler to handle this. But this would be the same thing as this. Good. And then what we want to do is validate that we have a new relocation. So we'll say assert that tasm.relocations.count equals 1. Oh, right, we can't do that. We have to say is equal to 1. And then we also want to assert that the relocation is its type is equal to relocation type dot. This would be, ooh, I forget, is it UPC relative I20? I think it is. Let's verify that. Ah, it is. Okay, good. So we need to assert that that relocation was generated and that it had the symbol name space. Good. So there it is. So this is going to take a little bit longer to implement because we have a few things. We have to handle this whole expression, create the relocation, and then the new instruction. So let's go to our, let's first run our unit test, of course, which will fail because we haven't implemented AIUPC. And then we go to our text assembler and we add support for it, AUIPC. And this will be ASM AUIPC because this is a very specific instruction with a specific requirement. AIUPC. There is our opcode. We'll grab that. And then we need to implement this new function. And what we'll do is we'll inject it like that. So now the first argument of AIUPC is a register, so we can just do this. But the second argument is not a register, it's a relocation or an immediate. So what we'll do is we'll call this new method I was mentioning, we'll call this expect immediate. like that. And what expect immediate will do is it will parse the content or the following symbols or tokens to see whether it is just a number, in which case we just inject it directly, or if it is a relocation, one of these PC-rel high relocations. So after having done that, we then expect the end of line. So we'll say asm.expect end line. And in fact, we do that in the branch as well. Good thing I got that. So having done that, then we can now assemble the actual instruction. So we say asm.u, I think it was. Let's go back and check. It is. And we need to make that internal as well. Oops. And we need to fix the content or the comment. This is asmu. We pass in the opcode. And then we have the register and the immediate value. So now we need to implement expect immediate, and it's going to be written over here. So how does this work? Well, we're going to have to take a look at the first token. So we're going to get the token, and we check to see if it's a number, then we just return the number and we're done. So if the token is equal to token number, then we return this dot current value, which is currently the value of that token. Good. And then if it's not, then we check to see if it's a symbol. So if token is equal to word, good, then we get the word. And then we check to see if that string is PC high. And recall that I wanted to add a percent sign, so we're going to check for percent sign PC rel high. Let's add that here and here. This makes it clear that these are directives. So we will say if w is equal to percent %PC rel high, then we also expect a left paren. So we will say expect token. We'll add a new expect method, and the token that we expect is a token dot left paren. And then we expect a symbol, which is going to be the symbol that we are to which we want to get the relative offset. So we'll say symbol equals expect symbol. Now we have a symbol, and then we expect a closing parenthesis after this directive. And if all of those things went well, then we will emit a relocation the way we do in the assembler. We want this relocation type. And in fact, we could just call this method because it's a public method. Let's do that. So we'll say asm.PCRelHigh, passing in our symbol. And we're good to go. And then we return a 0 because we don't know what that value is. At this point, the linker will fix it up using that relocation. Okay, let's implement expect token. Token. So if get token is not equal to token dot, actually no, it's expected, then we will write, excuse me, we will write expect We have one of these. Expect token is ourselves. Okay. All right. So then we'll just say error. And then otherwise we do nothing. Good. Now if the symbol, sorry, if the token that follows or in expect immediate is not a token word and it's not a number, then we have to report an error. So then we will say unexpected token and pass the token and then return a 0. So now we've handled PCRel high. So what happens if we run our unit test? It fails. And why is it failing? It's failing because the relocation never happened. So let's put a breakpoint in our assembler. Oh, right, we need a call expect immediate, don't we? Well, actually we do. We do call it. Now let's put a breakpoint here and see if we hit this when we run our unit test. So here we go. So we're expecting not a number, but a word. We get the word. The word is PCRel high. That's good. So now we expect the left paren. That's hopefully the case. Yes. Then we expect the token. The token is, or the symbol is space. And now we have emitted a relocation. That should have emitted relocation. Let's take a look and see if we can see the relocation in the assembler, the inner assembler. No, we don't. Okay. This just creates the relocation. I get it. We have to actually emit it as well. Okay, so we go back to the assembler here and look at AIUPC. Right, we need to add it to our relocations as well. Okay, that's easy enough to add to our code. So what we'll do is we'll say var rel equals that and then add it to our relocations. Nice. Okay, we were able to figure that one out. Let's stop the debugger and run all of our tests again. And if they all pass, which I hope they do, good. Then we run our program again. And we're slowly whittling down the amount of unresolved instructions. Okay, so here we get an error on line 33. So let's find out what that is. On line 33, that's this line. Ah, okay, so we have the brother of PCRel high is PCRel low, so we need to handle that kind of relocation as well. And also we need to make sure that add-I can cope with that. So we'll add a new unit test for this, and we'll call it, what do we call this? We'll call it add-I with relocation. Add-I with relocation, that looks good. We'll take this, put it in there. Oh, we're good. And then we will assume that this works the same way. PCRel low -4. And then what we'll want to do is find the AIUPC here and steal its relocation test, like that. And then the relocation is not going to be u PC relative, it's going to be I PC relative low 12. And this symbol, there will be no symbol name. There will be a offset. And I think that's supposed to be -4. Good. Good, good. So if we run our unit tests now, they will fail. Let's run them anyway. And now we implement AIU or PCRel low. So we need to change the add I assembler method, or ASMI, sorry. ASMI now needs to parse not a number, but an immediate. So we'll say expect immediate, and then that gets fed into here, and then our implementation of expect immediate now needs to handle PCRel low. And if that is encountered, then we have to parse it the same way that we parse the high relocation. But then, instead of a symbol, we're now expecting a number. So we need to expect number here, and we'll call that the offset. And there's our offset. And then we add it to our list of relocations, and we are done. So that concludes PCRel low. Let's see if we can get that unit test to pass. It's still failing. Let's take a look at why. Ooh. Okay, so we are getting a number back out that is too big. That's interesting. But I haven't seen that particular error before. So the offset may be it's an unsigned number. This is the problem. So what we'll do is we'll cast this to an integer, because this is an unsigned integer, but we are comparing it to a signed integer. So we'll stop the debugger and then run the test again with that cast. And the relocation value is 0. Is that expected? Where does the -4 go? That's my concern here. Because if we do a PCRel or PCRel low, yeah, we're hanging on. No, we're generating a local symbol, and then okay, so we need to copy this work. It's a good thing we looked at this then. Well, actually, no, we are calling PCRel low, so it will be doing all of this work for us. So the symbol, let's put a breakpoint here and see why this is not storing the 4 that we're expecting it to store. This is -4 coming in. All right, so insert pointer is 0. Our displacement is -4. So this should be, that's the name of the label that we generate. Okay, good. And the relocation that we are creating indeed has an offset of 0. Okay, so then we're not going to bother checking for it in our unit test. Let's get rid of that then. But we did assert that the relocation type is correct, so that's good. All right, let's run our program now, and we'll see that we've gotten past those pesky relocations. Okay, get rid of the breakpoint. And now what we're seeing is jump and link. So another easy, easy instruction to handle. We will add a unit test for it, of course, because we want to be sure that we're not going to run off the rails. It's going to be similar to the J instruction. But remember that jump and link takes a first parameter, which is the destination of the return address that we want to save when we're making a call to a subroutine. And that is how that is done. And so this would correspond to JAL1, my label. Good, good, good. So now we go and run our tests, which will fail, of course. And instead of waiting for that to complete, we'll just look for JAL, and we'll implement a special handler for JAL because it requires two parameters, not one, like J did, but they use the same opcode. So JAL does this. So we expect a register first, so that's the link register. And then we have the symbol. We need to emit our relocation, and we'll use ASM. Let's go back to the there it is. It's going to be very similar. But where do we do, what do we do with linked register? It's this slot here. Okay, good, good, good. You know, run our program. And it's all good. Let's see if we can get a few more instructions before we run into strings. SLLI, that's another I type instruction. Let's grab it from the source code here, and then we'll add a test for it. This is fairly boilerplate stuff at this point. Run test. There's our source. This is our intended. And that's how we do that. So now we need to go to our, I'll run our unit test first of all to get the expected error, but while that is grinding, we go to our assembler, look for SLLI, we steal the opcode, and then we go to our text assembler and find where we put this SLLI. There's our opcode, and it's an ASM I instruction, just like add I. Let's confirm that. Ooh, it's not. It's an ASM R encoding. Good thing I caught that. But that's going to be a problem though, because the I operand is not going to be necessarily a number. Let's let's make a function called ASM shift I to handle that particular case. Like that. So here we expect an immediate. Good. And I'll just add a comment, special case for shift instructions because their immediate values are smaller than the I type instructions. Good. See if we can pass our unit test. We can. All right. We're steaming along here. This feels great. Only have a few more minutes though before the hour is up. So here's a branch less than. In fact, I'm going to waive a unit test for this one because it's going to be very similar to BEQ. BLT is of the same family basically. But we'll go to the assembler and find BLT. There it is. So we'll grab that opcode. That looks fine. Then what else? All right, line 51. Something's happening on line 51 then. Let's take a look at line 51. Ah, right. We need to put some prefixes on these guys. Let's run. Load immediate. This is our shortcut for add I when the left and we're basically loading a small immediate to a register. So we'll add support for that in our assembler too. We'll use it here. And so what we'll do is we'll say, we'll frustrate a unit test because this is a little, our syntax is slightly irregular here. So we'll say test public void tasmli to load immediate and run test. And we'll take the sample that we have here. Let's make this more interesting. And this should work the same way as this instruction. And of course, by running this, it won't. So now we need to add a handler for load immediate. And the load immediate will have its custom implementation. So I will write it like this. And we'll just ignore the opcode because we'll be generating it ourselves. So this is a special case. We will expect a register, which is the destination register. So asm.expect number. We really should be calling this expect register. Maybe in a future session I will rename those. But then we also expect an immediate. So we'll say asm.expect immediate. And then we will call the underlying assembler asm.asm. Okay, let's see, what are we doing here? We're calling li with reg and immediate, just like that. Good. Good, good. Let's see if that passes our unit tests. Excellent. And now we run our full program one final time. And let's see what error we are stuck at. On line 56, there is an error. Ooh, I also have forgotten that we need to expect an end of line at the end of this guy. So let's make sure that we have that in place. All right, so let's run our program again. And let's see what error we get. 956, unexpected word. All right, that's just where I wanted to end up. But let's take a look at this instruction here. So we want to load into register 17 a symbolic constant. And we haven't implemented those yet. So next session, we're going to look at how to cope with symbolic constants. How do you express constants in an assembler? And naturally, that will be very, very useful because right now we're dealing with a lot of explicit numbers everywhere, and this can become very hard to understand in a large assembly language program. So in the next session, what we will do is we'll implement support for symbolic programs or symbols, symbolic names, so that we can use them uh, instead of these opaque numbers that we see scattered everywhere. But I've run out of time, so without further ado, thanks so much for watching and tune in for next time. And also remember that the source code for all of these experiments, all of the work that I'm doing here is available on GitHub for you to browse. And also, I'm deliberately leaving some code unimplemented. Should you feel the urge, don't be shy. Send a pull request if you want to implement part of the assembler. Uh, Pull requests are gladly accepted. Okay, goodbye for now.